Modo cheio, tá bom. Aqui, esse?
Aqui.
Modo tela cheia.
Tá certo?
Tá certo, Alexandre? Obrigada. Avisa aí quando for começar que a Raquel ouve. Eu acho que tem uma câmera aqui. Pessoal, boa tarde. Agradeço os nossos convidados, agradeço a professora Raquel, né, por estar aqui coordenando hoje o seminário. E nós vamos, então, hoje em especial, termos 2 seminários e teremos bolo. Raquel, muito obrigada. Bolos, olha só. Bolo 50.
Eu vou falar inglês agora, porque ele entende português, mas ela não, só inglês. Francês. So I'm switching to English to present you. So first, thank you, both of you, to accept. So we have 2 seminars today. One is by Inès Vongpaseut. And she is a PhD student at University of Toulouse. And she did a bachelor degree in geology in Paris 7 University, and then a master's in atmospheric science in Toulouse. And she is studying for her PhD simulation of aerosol microphysics, electricity interactions in deep convection systems. And she will present just a little part of her study, and then after that we'll have another presentation from Thibault, and then I'll present Thibault again. Thank you. You can use that.
Yeah. So thank you, everyone. So thanks, Rachel, for.
Vamos aí. Vamos aí.
So you need to choose speaker.
Yeah. Okay.
Or put quote.
Yeah. So today I'm going to present the work I did during my first year of PhD. So it is about the influence of ice collection on cloud electrification and lightning activity in simulated thunderstorms. So for a bit of scientific context, here you can see like the different physical processes that can take place in the thunderstorms, and which I'm focusing on. So we can start on aerosols that can add cloud condensation nuclei or isolate nucleating particles. So they activate into primary hydrometeors, so cloud droplets or ice nucleating particles. So then they evolve through different microphysical processes in the storms, and then it will be the ice particles that will electrify the cloud, so mainly by the non-inductive process. So each hydrometers acquire charge, and then they separate at the cloud scale through the dynamics and also the sedimentation, and this will create an electric field, and when it is too intense, so lightning are triggered to neutralize the charge. So in my PhD, I'm focusing on the impact of ice crystal formation on cloud electrification. So looking first on at the aerosols, so acting as CCN or INP, and then on secondary ice collections, so which arises from already pre-existing ice particles. So to do that, we have the electrical scheme, an explicit electrical scheme, so named cells. It is able to simulate the electrical bulk charge carried by each type of hydrometers, and also the lightning propagation. So it was recently coupled with a crazy tournament scheme named Lima, and this scheme is able to compute the non-inductive charge separation, the electric field, and also the 3D lightning propagation. So going back to the charge separation, so named the non-inductive one, it is known to be the main mechanism that can electrify clouds, and it's an exchange of charge during collision between an ice crystal and GoPro during its firing. So this is based on different laboratory measurements. So for example, here you can see the different lines are different studies, and they give the signs and also the amount of charge acquired by hydrometers, depending on the temperature here and the cloud water content. So for example, if you are in the first zone, The vapor will be charged negatively and the ice crystal positively. And in contrast, here, the vapor will be charged positively and the ice crystals negatively. I will present quickly my model setup. So I'm using the Meso-NH model, which is it's developed in Toulouse. And I'm using first the microphysics scheme Lima. It's a crazy tournament scheme. So we only have the number concentration of ice, rain, and cloud droplets. So then we use the electrical scheme cells with the Takashi 1978 parameterization, and also a 3D tolerance. So we choose to simulate 3 different cases to have different environmental conditions to see how storms can react to ice production. So here they are named warm, mid-warm, and cold based on their cloud-based temperatures. So for the warmest, it's 22 degrees, and the coldest, 11. So this will impact the thickness of the warm cloud face, and then impact the microphysics. So there are idealized cases, which means that I'm using radio sounding, so based on the papers, and I'm initializing all the domain homogeneously with this radio sounding. So to assess the impact of ice production on cloud electrification, I did some sensitivity tests. So first on the aerosols concentration. So I varied the CSN concentration over 5 values and the INP also over 5. And I did one simulation for each pairing of INP and CSN concentration. So it results in 25 simulations for each idealized case. So it is good to know that in our model, there is a secondary ice production that is by default activated. So it is the splintering lumiriming, so the Hallett-Moser process. So it is when we have supercool cloud droplets that wind onto a bubble, and it can emit some fragments. So this process is active in all the previous simulations. And then we have 2 other secondary ice production parameterized in our model. We have the collisional ice breakup, which is just like a mechanical effect when 2 ice particles collide, so it emits fragments. And the last one is the raindrop shadowing freezing. And this is when a raindrop collides with an ice crystal, so it freezes and then can emit also some fragments. So then I also did sensitivity tests where all the 3 C processes are not activated, and the last one when we have all 3. So I'm going to present some of my results, and in the remainder, I'm only presenting results in the convective zone and during cloud electrification. So here we have the sensitivity on aerosols concentration on the parameter cloud water content. So you have some vertical profile. So each color represents 1 INP concentration, and all the lowest INP concentration had the same behavior, so they are all in blue here. And then you can see a colored area, and this will represent the sensitivity to CCN concentration. So when we have low CCN concentration, we have a low cloud water content, so we are the left side of this colored area. And then when we increase CCN concentration, cloud water content also increase, and then we get to the right side of this colored area. So what we can see here is that at low altitude and also at low INP, we have less cloud water content, for example, here. And this is because we are warm cloud process are favored, so we have more raindrops and so less cloud droplets. And then at high altitude, what we can see is that at lower INP concentration, so in blue, we have more cloud water content, especially in this case. And this is because we have less vapor mass, so less rhyming, and then we get more cloud water content at colder temperature. So we can see here that we have different amounts and also different location of cloud water content in different storms. And this will impact on where the non-inductive charging process can occur, and then also the sign and the amplitude of charge acquired by each hydrometeors. Then on the ice crystal number concentration, here you have a different vertical profile. So each column will represent one INP concentration, so going from the lowest to the highest, and each row is one idealized case. So what we can see here is that we have many differences, but mostly at higher altitude, so at around minus 35 degrees Celsius, and then also near the isotherm 0 degrees. We can see different behaviors. So first, we can see that when we increase CCN concentration, we also have an increase of ice crystals. So here we can see it in the lower INP concentration and also up on the cold case. But we have some exceptions and get higher ice crystal number concentration for medium CCN concentration. So for example, here for the green curve, it is for CCN concentration of 5,000 cubic centimeters. And then the second behavior that we can see is that at higher INP concentration, so here, we have the same ice crystals number concentration, whatever the CCN. So they have here the same concentration. So to explain those different behaviors, we can look at the ice production process tendencies. So here you can see that in color and in values, it is the ice production tendencies summed in the storm, so in the convective zone. So for each CCN concentration on the x-axis and INP concentration on the y-axis. We can first focus on the first row, which is the heterogeneous nucleation. So it's the INP that can activate into ice crystals. So logically, we can see that when we increase the INP concentration, we also increase the ice production. Then focusing on the second row, it's the homogeneous nucleation. So this is when small cloud droplets can be transported at colder temperatures and then they can freeze. So what we can see here is that when we increase the CCN concentration, so we get to the right side of the plots, we increase the ice production. So we have smaller cloud droplets that they are more easily transported into the ultra. And then when we increase the INP concentration, we can see that the ice production is less intense because we have water vapor, a competition for water vapor between ice crystals and cloud droplets. The last row is about the atmospheric processes. So it's the splintering of GoPro during its priming. And we can see something a little bit more complex, is that we can have a CCN concentration threshold. So for example, if we focus on this case, when we increase the CCN concentration here up to 8,000 cubic centimeters, the ice production increase. But for higher values of CCN concentration, so here 10,000, we decrease the ice production. So this can be explained by the smaller droplets that are formed when we have a CCN concentration higher, and then it's less effective for the rhyming of GoPro. So the different behaviors that we saw in the ice production tendencies can be seen also on the electrical activity. So here it's the same plots from the last slide, but we have the total flash number during the 1 hour simulation. So we can see at lower INP, so the first 3 rows, that when we increase the CCN concentration, we increase the electrical activity. And then at higher INP concentration, we have thresholds, so linked to the high atmospheric processes. It ranges from 5,000 and 8,000 cubic centimeters. For example, in the mid-warm case, the threshold is at 5,000. And then when we get to higher CCN concentration, the electrical activity decreases. I will talk shortly about the sensitivity on the secondary ice production processes. So here it's vertical profile of ice crystal number concentration. So each color represents the sensitivity test. So looking at the atmospheric processes, so it's the black line. We can see that it's always important and increase the ice crystals number concentration. For example, here also, and here. And then for the raindrop shading freezing, it's only active in the warm and mid-warm case. So it's the orange line, so we can see an increase of the ice crystal number concentration. But in the cold case, we cannot see it, but the black and the orange line are layered on top of each other. So the raindrop shading freezing doesn't produce ice crystal in this case. And then the collisional ice breakup, so it's the green line. It always enhance the ice crystal number concentration. So the trend in ice crystals number concentration is also reflected on the electrical activity. So when we activate SIP processes, we tend to increase the ice crystal number concentration and so the electrical activity. So to conclude, we saw that the lightning activity, but also the electrical structures that are not shown here, are sensitive to aerosol concentration, both as CC and NINP concentration, because they will impact the ice production processes, so mostly the homogeneous nucleation and the high atmosphere processes. And then for the secondary ice production, we can see that depending on the process, it is not always active in certain environmental conditions. So, for example, the raindrop shadowing freezing needs enough deep warm cloud phase. And when we take account of the SIP, we tend to increase the ice crystal number concentration and so the electrical activity. So that's it for my presentation. Thank you.
So I'll take a little round of questions.
Yeah.
Hi, very nice talk. Can you comment a little bit on the electrification scheme that you have at
Yeah.
Because you showed Takahashi model.
Yes.
So how do you compute the number of ice particles that will collide and separate to get that? Because you cannot have accretion, neither accretion. It has to be
the only
collision.
vapor deposition.
No. When you have like the collision between ice crystals, in order to get the charts, they have to separate.
Yeah.
So you have 10,000 particles. So how many of those 10,000 particles will collide and separate? So how do you compute that?
I think this is computed with the collision kernel, and depending on the size of the vapor and the ice crystals, we can know if they fragments or not. I think it's depending on the size.
But you said you have a total concentration, not size.
I think the mean size of the, since we are in a two-element scheme, it's like the mean size of one grid cell.
I think they get the mean size on diagnostic, on assume shape and geometric mean.
And the last one that you said INP and CCS.
Yes.
So what's the size of the aerosols? Because they impact a lot.
Yeah. So to keep things simple for these preliminary results, we have just one mode of each aerosols. So we haven't seen for this study, I have not seen the impact of size. I think it might be a good idea to, with realistic cases, with aerosol measurements.
Or you just constrain.
Yeah.
Because if you have smaller ones, you have smaller droplets that will be frozen at higher levels.
Yeah.
If you have large ones, it will be at lower levels.
Yes. Yeah.
So it's going to change everything.
Yeah, sure.
Any other questions? Pode fazer em português. Não? Não?
Se você quiser, eu faço mais.
Pode fazer?
Se você deixar.
Eu sou inquisitora.
The comparison. The last one, so the total flashes is computed as you get the electrical field that reaches the breakdown. That's how you
Excuse me, can you?
how do you compute the lightning flash?
Yeah.
To get the total. How explain this? Because I know it, but they don't.
So the electrical scale, so we have the lightning propagation. They are computed based on a cell definition. So we have to have enough intense electrical field to trigger a flash. And then we have a fractal law to compute the different branches and segments of one flash. So first we have the propagation of a vertical velar, and then based on how far we are from the triggering point, we have a fractal law to know how many branches we can have to compute and to neutralize the charge.
Okay, so using that.
Yeah.
I have one question. How realistic it is? The highest INP you put is 1,000. How realistic is that?
We chose extreme values. So usually I think in a normal condition, average conditions, I think the INPs are mostly at 10 per liters. But when we get like dust events or maybe like fires, we can have more INP concentration. We chose an extreme value to see how it is.
Okay.
Veja se tem alguém no chat.
Eu tenho uma pergunta.
Sim.
Vou perguntar em português. Qual o software que ela utilizou para fazer os gráficos e a estatística?
He is asking which software did he use to make your figures and statistics.
I'm using Python.
Python?
Yeah.
I think you asked for the package.
Oh.
Later.
Vê lá, por favor, Raquel, se tem alguém.
Não, não tô no Meet, só tô no Google. No Google, no YouTube não tem.
No YouTube eu tô também, não tá?
Não?
É melhor não, olhar aí.
Não, ele está no
Google
Meet.
Meet aqui.
Não, tá no Google. Tá no,
No YouTube não tem.
no YouTube.
Mas tem o Google Meet, que tá aí.
Achei que cada um estava em.
Que eu não entrei
Não,
no Google
ela
Meet.
não sei se tá no Meet. Vai no Meet.
Que às vezes tem alguém aí. Vê lá, não.
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 Okay, so thank you, Inès, very much.
Thank you. Bom que tem 7 pessoas também. Eu tenho multimeios, o Marcos e mais 7.
Pô.
Não tem ninguém online?
Não, tem. Tem 7, porque um é o multimeios, tem 8, o outro é o Marcos. E no YouTube só tem a Carla. Acho que ela ouviu falar que tem a Carla. Não apareceu mais alguém, mas acho que
Mas quem for bem perto, não sei.
Vocês estão vamos ver se tem raio.
Ah, sim, hoje é para descer a água de novo.
Deixa eu ver. Que bom, né? Não podemos nem reclamar.
Até ontem tinha chovido 80% da chuva do mês. Cadê meu informante?
Bom, agora nós temos nosso segundo palestrante de hoje, Thibaut Dahout. Ele é pesquisador do Laboratório de Aerologia, do CNRS, na França. Também é professor na Universidade de Toulouse. E ele fez físico aplicado pela Universidade Pierre-Marie-Curie, Paris 6.
Yes, right.
E também o mestrado na mesma universidade em Oceano, Atmosfera e Clima. E depois o doutorado, também em Oceano, Atmosfera e Clima, só que pela Universidade de Toulouse, o Paul Sabatier, que é onde você dá aula hoje, né? Também, ele é professor hoje lá também. E no meio de tudo isso, ele viajou o mundo.
E aprendeu português.
Em uma dessas viagens, aprendeu português. Foi para a Austrália, aqui no Brasil, Estados Unidos, Austrália de novo, a Alemanha, enfim. E também no Café Brasil de novo, que foi onde nós começamos toda a colaboração aqui. Então, muito obrigado. Bom, pode começar. Tá.
Muito obrigado pela apresentação, introdução. So in English, so good afternoon everybody. I'm really pleased to present today my contribution to the collaboration we are building with Raquel here between the University of Toulouse and the University of São Paulo. So my contribution is more a dynamical part. So I will speak today about the transport by deep convection over Amazonia and the sensitivity of this transport to the organization of the convective systems. And I selected this satellite image just to show you a typical situation of Amazonia full of convective systems. And one of them is producing a cold pool that you can notice with this arc just here, which is one key process for the organization of the systems. And in this presentation, I'd like just to mention that there are contributions from Elena and Bastien, who were in front of me and work on the simulation that I will present. Just giving some context about what we know very roughly about the Amazonian system. So they are, in general, they produce weaker updraft than what you can find in mid-latitude, but they still can organize and be quite intense during the transition and the wet season. And when we simulate them, if we use kilometric resolution, we tend to produce too strong updrafts with too large vertical velocities, and it's getting a bit better when we go towards final resolution, like hectometric resolution, so about 100 meters. Something we can see in this vertical profile of vertical velocity with the measurements from the Amazon in dark green and simulations with either kilometric or hectometric resolution with other colors. And here I show also two vertical cross-sections to show you that when you use different resolution with the model, you also produce quite different organization of the vertical transport. As you can see, with kilometric resolution, you can produce quite nice plume of here it's a tracer that is on it's like a tracer emitted at the surface, but then you transport efficiently air masses from the surface towards the upper troposphere, while at hectometric resolution, you tend to produce more warm bubbles that are one after the other and mixing a lot with the surrounding air, so the transport can be much weaker or more dilute. So I will also address this question of the impact of organization to the transport.
What is the resolution in the vertical?
In the vertical. So for this one, it's coming not from one of my studies, just a study intercomparison of model from Verbal et al. I don't know exactly the vertical resolution in this case. I guess 100 meters, something like this. But most of the time, it's depending on the altitude, you get final resolutions toward the surface and 100 meters more in the upper altitude. But I don't know exactly what was used for this counts. And so to investigate this question, I used some cases from a previous field campaign, Café Brazil, that Raquel mentioned, is where we met Raquel, Isabella, and also Michael. And it was happening in 2022 in December and January 2023. It came in the last part of the campaign. So this campaign was mostly focusing on the chemistry of the atmosphere and the generation of new aerosols, but also the role of convection in this process. And I found that it's very nice to sample the transport by convective systems. So it's perfect to find some realistic cases to investigate the sensitivity of transport to the organization. So it took place nearby the Alto Tower in the Amazon, And we had also an aircraft from Germany that flew from Manaus all over Amazonia. And I selected finally the flight of 18th of January 2023, as it offers some typical convective systems that are presenting some very large cold pools and somehow a squall line organization, as we can see sometimes over Amazon. Some words about the configuration I used to simulate this. So I used the Meso-NH model, which is a model that we developed in France and worked together with other European colleagues. And I'd just like to mention that I did the simulation of a new supercomputer called Adastra, which is accelerated with GPU. So it's very nice because we can do a very large simulation, but it's also tricky because sometimes we don't very understand how it works and where the errors come from, even the technicians, the engineers who are working with us. So it's a bit of a challenge. But then we managed to do a series of simulations over Amazonia. They are all over the same domain, like 800 kilometers large, square. And I use different resolutions, so 1.6 kilometers, 800 meters, 400 meters, and 200 meters. So there are 4 simulations with the same domain. And all of them last 1 day, 24 hours, starting at midnight the 18th of January. And in contrast with what Inès just showed you, I don't do idealistic simulation, but realistic one. So I don't have the same profile all over the domain, but I use ECMWF analysis to initialize my simulations and to force them on the borders. I also mentioned that I don't have any convective parametrization, not even a shallow one. And I did this even at kilometric resolution to have a similar setup for all simulations. I use also, in contrast with Inès, a single moment microphysical scheme and turbulence parameterization with prognostically. So just to describe you what is the situation on the 18th of January. So over this small domain, here I show you some brightness temperatures from the GAUSS satellite at around 10 microns. So you have deep convective systems that are in the northeast of the domain at 13 UTC that day, but then they decline and tend to produce an area that is with weaker convection here, and you have new convective system triggered in an arc and then propagate towards the southeast. So I just draw this line to show you the arc where you have less convective activity towards the east and convection propagating southwest. So when I simulated it with the highest resolution I had, so 200 meters, then you can see relatively similar behavior with very large deep convective systems in the northeast. It has not the same orientation, but it's still declining and producing an arc of convection here that ends up into a squall line, relatively large squall line, propagating towards the west and the south. So here there are almost the same maps that I show you just on the top, mentioning that the systems that are very large, so 500 kilometers wide here and 80 kilometers large squall line. So we definitely need a very large domain to simulate them, and so it's a challenge to use at the same time fine resolution and large domain, so very large grid. If I want to compute the organization of the system here, I used here the RUM metrics. I can tell you a bit more maybe at the end if you have any question about this, just to quantify the organization. And I divided it by the mean surface of the object. So the highest is the value of this index, the more organized it is. So to have an idea is when you have like a large object that are clumped close to each other. The opposite, it's low when you have like many small objects all over the place. And for all simulation, what you can see is that the organization is increasing until 14, 15 UTC, and then there is a sharp decrease, and this is more intense, this decrease when you're on kilometric resolution. And just to understand what is going on, I just show you here other time series all over the day also. So on the top is the total area of the object, so that are defined as area where you have ice water parts larger than 1 kilogram per meter square. in these maps. So you see that the area is actually not so much changing all over the day, but what is changing a lot is the number of objects, which is increasing a lot after 14 UTC. And it's actually much larger at lower resolution. And just to give you an illustration, here I just show you two maps, one at 1.6 kilometer resolution and one at 200 meter resolution. And you see that indeed you have many more cells at 1.6 kilometer resolution, while at 200 meters you have this arc and a nice clear sky area towards the west. So the organization is much stronger when you have a finer resolution. Also, something which is different is that we end up with a scroll line organization at 200 meters, and it's something you don't get at all at this resolution, 1.6 kilometer. Actually, we get it at the two finest resolution, 200 meters and 400 meters. In terms of range, it's the same. You will see so the same behavior. Here is just to show you the four different resolution, going from 1.6 on the top left. You see again like a population of cells all over the place. Atto is here and Manas is there, by the way. And when you increase the resolution, you see little by little the organization happening with the scroll line being more and more defined, and also the clear sky area, which is much more important at final resolution. The same here, it's for the rain, the rain, so just a zoom between the two resolutions that produce the scroll line. You see that even at between these two, you have a better definition or more clear definition with the finest. If we look now to not the cloud, but the convective cells themselves, so I use another metric here, is the global water path, to see really where the convective cells are. And then I can do also identification of the clusters to see how they are organized over the domain. And this is what is represented below. And if you compute the organization based on that, you see that actually the peak of organization is much earlier than for the cloud. You have a peak around 9 or 8 UTC. And then it's already quite low when you have the maximum of organization for the clouds. So here I compared the two. So you see that there is kind of a delay, and this delay is actually due to the fact that the convective cells bring up some like the humidity and produce a lot of hygrometers, and this is because of the persistence of the handle that actually the cloud organization is peaking about 6 hours later. So now this is again the dropper. You see the dropper water path. You see the contrast between 1.6 kilometer and 200 meters. And just looking now at the impact on the transport. So I just produced different profiles to look at the updraft that are defined as region where the vertical velocity is larger than 1 meter per second. So if you look at the right profiles, these are the total updraft mass flux, and you see that it's actually larger in red for the simulation, which is the finest, 200 meters. And when you go to coarser resolution, it's lower and lower. And then to understand why, we looked at different aspects. So on the left, it's the intensity of the updraft with the vertical velocities. It's the 99th percentile. And in the middle is the section of the updraft. And the surprise was that actually the mass flux is larger, but this is not due to more intense updrafts. They are actually weaker at atomic resolution. But to larger updrafts. They are weaker but larger, so the mass flux ends being larger. Something you can see also with different thresholds to define the updrafts. So here it's with 2 meters per second, but it's the same results. So just to conclude, we found that organization is quite sensitive to the resolution. We use it between 200 meters and 2 kilometers. With a larger organization and much nicer scoreline organization at high resolution. And we can wonder what is, how can we consider this when we see that there are more and more studies using GSRM. I don't know if you are used to this here. Have you ever heard? No? GSRM are a global model with kilometric resolution. So they manage to simulate explicitly the convection on a global scale. it's very nice actually, but they are still at kilometric resolution. So with at most 2 kilometers, sometimes exceptionally 1, but most of the time is about 5 kilometers. And we found that here, that using this kind of resolution, actually, the organization of the system is not the same as when you use ectometric resolution. And there is quite a sensitivity still at this point, so we are still not converged, and we are not really sure about the transport made by the system when they are simulated at kilometric resolution. So also we found that the transport is sensitive to this resolution based on this Amazonian case, with larger transport at high resolution, and this is due to larger updrafts that are actually weaker. And there are relationships between the transport and organization, which is something I'd like to investigate more in the future. But keeping in mind that it's quite different when you compute the organization of the cloud, where you see the importance of the anvil, and when you look at the organization of the convective cells. So that's mostly what I wanted to show, maybe mentioning that there are upcoming space missions that could help us to investigate this. So I'm part of the scientists who are designing the CL mission with the objective of looking at cloud at tens of meters. So it's really fine resolution, much finer than what I presented here. But we will see the cloud envelope. We will look also at the water vapor around the cloud that could allow us to maybe assess the transport by these convective systems. And also instruments looking at the electric activity, also at very fine resolution. And I'm kind of curious to see how we can understand better the dynamics based on these electric measurements. There is another mission called Komodo, which should appear later to measure the ice mass flux. And Earthcare, I put it at future, but now it's in the space. So, but we haven't used so far the measurements, but I'm very curious to see it in the future. Yeah, just mentioning that I'm also supervising some PhD. So one of them will be in computer soon with Isabella, and looking at the role of deep convection as it produces linox that are key for the production of the aerosols in the upper troposphere, trying to model this after the investigation based on observations. And there is also a new PhD student who just started and who will look with me to the role of transport for the formation of these new aerosols, as you need to mix at the same time species emitted by the forest and nitrate oxides emitted by the lightning. So thank you for your attention.
Taking pictures and that. So, have any questions for Thibaut?
So hello Thibaut, thanks for the presentation. And so I was trying to figure out the effect of the resolution on the organization, because you showed that coarser resolution, there are more clouds, that are less organized and more intense updrafts, and then with finer resolution, we have fewer clouds that are less intense but more organized. So do you think the entrainment plays a big role on organizing, not necessarily the large clouds, but the other smaller clouds in the field? Oh, yeah.
I guess so, indeed, because what is changing a lot when you change the resolution is how you represent the turbulence. And I guess it's much better to represent it at ectometric resolution, so you have more eddies. Even the small eddies or the relatively smaller eddies are better represented. So you can dilute more the weak updraft. So it's like more difficult for the updraft to rise. But once they manage to rise, then they are stronger. And as you resolve better also these eddies, they can entrain more and then bring more mass up there. And this could contribute, for instance, to the fact that they are actually larger when you are using finer resolution. So I think indeed the entrainment can be a key measurement, a key variable to estimate from one simulation to the other to see what is going on and why we have a larger transport from resolution.
Just a follow-up. Sorry. So as you go down in resolution, you get more entrainment, but then is there a way of knowing which is the optimal resolution when you compare to observations, or?
This was still preliminary work, but indeed it's very important, very key. As I'm actually using a realistic case based on observations, based on the campaign, I really want to use more observation to constrain better and to know which of the simulation is actually the closest to the observation, to the reality, and even to be able to assess how close it is to the reality. Because even if we have one which is close, maybe it's still producing, for instance, too strong vertical velocities, and it's why I'm really looking forward to use also like measurements we made from Campina to see how the model is behaving. Is it producing the good vertical velocity, the good transport? And it's the chance we have with this campaign. Yes.
I lost information. Did you use the same domain for all simulations?
Yes.
800 kilometers. And you use the ERA 5 to boundaries?
It's not ERA 5, it's the analysis. Okay. Not reanalysis, but analysis.
The analysis, the daily analysis that
exactly.
Okay. How is the time step that you
update
the boundaries?
I think it's 1 hour, if I remember correctly. Yeah. If I'm correct. Yeah. Oh no, the analysis is every 6 hours, isn't it? Or maybe it's 6 hours.
6 hours?
Yeah, 6 hours, you're right. Yeah, in between is
you notice some many discontinuity between the domain and the boundaries or not?
Not so much, yeah. You mean when you look at the map, if we have some, because indeed it's something we could have most of the time. Or
this is all domain?
This is the whole domain.
Okay.
Indeed, it's the borders of the domain. The question is, do we see any margin around this? And this is something I get very regularly when I do simulation based on analysis, because the analysis are, if I remember correctly, 9-kilometer resolution. So it's like jump when I'm doing a simulation with hectometric resolution. And what can happen is that you have a very smooth field from the border where the wind is coming in. And if this is happening more when you have less intense convection. When the convection is very intense, actually it's producing a lot of turbulence, and like it's and you don't see anymore this weak or this smooth field coming from the entering border. So I think it's because it's quite intense that we are safe from this.
Questions?
More questions?
Aqui, ó, lembra de olhar lá no... Não entendi, só tem pessoal.
Não? Pessoal, vocês estão muito tímidos no...
I have to admit that it's the first time of my life that I'm at the same time on Google Meet, on YouTube, and on what? On Google what?
No, it's the Google Meet, YouTube, and here.
It's crazy.
It's very organized.
Yeah.
I don't, usually in the past we also transmitted in Facebook, but I think...
yes, now they continue.
So you are in Facebook. So you are in Facebook.
Wow.
We use both YouTube, Facebook, and books.
Google Meet.
Google Meet.
Any other questions? I have one. So based on all of that, how do you expect the mixing of all the gases to form the new particles in the upper troposphere, and also the reverse, how if they come, they can get all the way from the upper troposphere to the boundary?
Show. Just try to find some. Yeah, so the question is how important is the mixing for the transport of this species? I should use the tool that is again. So my last chance to use it, actually. So it's actually one of the big questions we will try to address with the Axel work. Like we know that you have species emitted by the forest, species emitted by the lightning. All of them are key for the formation of the new particles, and we don't know at all whether they are just mixed in the cloud as the first ones are transported, and maybe the lightning is actually emitting the lightning knocks right in the same air masses, and then they're already mixed, or are they emitted in other masses, and then you need some like mixing in between by the eddies, for instance, in the clouds, and where is it happening, or intensities, and when it's there are all questions that we would like to investigate with the simulation, or with simulation that have the same resolution as the one I showed, so that we are able to represent these edges for the turbulence and actually track the air masses in the system to see what is their history before arriving in the upper troposphere, and there they produce the aerosols. But yeah, it's still a mystery, and we hope that the modeling can help us to understand better. And also for the other contribution here, I cropped the picture, but there is another big mystery is what happened to the air particles when they are formed up there. When do they serve as cloud condensation nuclei, as Inès showed, and we don't know how they are transported down to the surface. Is it via in-cloud downdraft, like we show here, or is it like outside the system in like the compensating subsidence? We don't know. So we hope to be able to answer this with the simulation, but the second part is less sure, because if it's happening at very large scale, maybe our domains are too small for that. So we will see a bit later with Axel.
Okay. Thank you.
What about the background flow that you consider in your simulations? Does it is it provided by the boundary conditions, or?
Yeah. Yeah, the situation of Amazonia, you have a very shared atmosphere. You have air masses that are flowing in very different directions. I think it was coming from the Atlantic, so from the northeast, close to the surface, and it was completely opposite in the upper troposphere, and in between you had another one. And in our case, so to get this this shear atmosphere, actually we have the initial situation that is already shared, and also the boundary conditions that are actually shared as well. And all of them are coming from the European Center analysis. So it's based on that that we have the share as observed, or as close as observed as possible. And this definitely also contributes to the organization at some point. So
Yeah, because these mesoscale convect systems are well known to rely on the shear flow.
Yeah, the shear.
To propagate.
Mm-hmm. Depending on the shear you have, you can propagate faster or not, or organize better. But
A gente tem bolo lá, vamos encerrar isso.
I have a question, but can I speak in Portuguese, please? Because I think nervous when I speak in Habituro. Eu vi que você mostrou mapa diferenciando uma execução de 200 metros e 400 metros, né? E tinha diferenças. Que processos daquela execução de 200 metros não estão sendo
Resolvidos.
representados, né? Naquela de menor resolução? Porque tem um trabalho de Pachini e Stevens, 2023, eles fazem simulações com o modelo Icon, e naquele trabalho eles mencionam que chega um ponto em que você apresenta a resolução espacial, mas não tem muita diferença, sabe? Chega um ponto em que, por mais que você apresente a resolução espacial, ele vai conseguir mostrando quase o mesmo.
Se lembra quais eram as resoluções?
Ele faz uma diferença entre 5 e 2,5
quilômetros, ok.
Que tá fora do que ele analisou.
Ele é mais...
Obrigado pela questão. Então, aqui estou olhando as resoluções um pouco mais finas que isso, para ver se está ainda bem com essas resoluções quilométricas. Na verdade, o que a gente vê é que com as resoluções mais altas, mais finas, a organização do sistema é diferente. Então, mesmo se as diferenças são poucas entre 2.5 e 5, mas não quer dizer que isso é o que aconteceu, porque quando você acrescenta mais ainda, a resolução está diferente. Então, a sua primeira parte da questão era sobre os processos, né? Os processos que estão acontecendo dentro da nuvem e que você vê mais com 200 metros, por exemplo. Então, o mais sensível vai ser os turbilhões, né? Vou parar. Porque esses turbilhões, quando você usa quilômetros, você vê só tipo, os maiores. Mas com 200 metros, você vê muito mais uma cascada de turbilhões que pode misturar muito mais as massas de ar. E também um processo importante, mas que não tive oportunidade de estudar aqui, é as piscinas de ar fria aqui. Deve ser muito diferente de uma resolução para outra. E com 200 metros, espero que está resolvido de um jeito melhor, mas preciso ver ainda um pouco isso, especialmente com observações da Torre Ato, que não usei tanto por aí.
Sim, e aí vai ter importância em trazer alguma coisa, ou da alta troposfera, ou mesmo o NAX de dentro da nuvem para baixo da atmosfera. Ok, mais alguma pergunta? Não? Então tá, muito obrigada, Tibon. Obrigado a todo mundo que está online. E tem bolo aonde? Auditório ou Seminário?